Okay, so we're going to introduce moles and concentration now. So you've come across concentration before when we've talked in terms of grams per dm cubed. Okay, so we looked before at grams per dm cubed, and we learnt that that meant the mass in grams dissolved per decimeter cubed. So you know in maths, for example, x to the minus 1 means 1 over x, so we could think of that as per x. So dm to the minus 3 means 1 over dm to the 3, so that's like per decimeter cubed. And we should remember that 1 decimeter cubed is 1,000 centimeters cubed. Sometimes people get a bit muddled about that, but remember that 1 decimeter is a tenth of a meter. Okay, a tenth of a meter is 10 centimeters cubed, so 10 by 10 by 10 gives us 1,000 centimeters cubed. So 1 decimeter cubed is 1,000 centimeters cubed. So our concentration that we learnt about before, just to recap there, is the mass dissolved per decimeter cubed or per 1,000 centimeters cubed. Why does it matter that we have labels of concentration? It's so that we can compare different solutions even if we don't have the same volume of them. So it's always the concentration if you'd scaled up to have enough to make 1 decimeter cubed of the stuff. Whereas you know in the lab we usually have bottles that contain about say 250 centimeters cubed or so. Okay, so it's allowing comparison. Now we've learned a lot previously in year 10 about moles. Now we know that lots of different substances have lots of different molecular weights. So in order to be able to look at reactions, we need to be able to look at the number of moles, because that's actually comparing the particles, number of particles. Remember that 1 mole was 6 times 10 to the 23 particles. So if we can compare a ratio of moles, it means we're comparing the ratio of the particles there. So what we need to learn about today is how to use moles and concentration. So we're going to look at new units, and that's mole dm to the minus 3. Now along the same idea as our grams dm to the minus 3, we can decipher that. So it means how many moles we've got per decimeter cubed, so per 1,000 centimeters cubed. So a typical label on a bottle might say, so let's say with our hydrochloric acid that we've had in the lab. So our hydrochloric acid in the lab might say on the bottle that it is 0.2 mole dm to the minus 3. So again, we need to decipher that. What does that actually mean? So that means that if we had 1 whole decimeter cubed, we would have 0.2 moles in it. So 0.2 moles in 1 decimeter cubed, which is equal to 1,000 centimeters cubed. Now when we measure out quantities in the lab, we rarely measure 1 dm cubed. We leave that to the realms of the technicians when they're making up tons and tons of solutions for us, and we use smaller quantities. So we might have done an experiment where you were asked to measure out 25 centimeters cubed of 0.2 mole per dm cubed hydrochloric acid. And what we need to learn today is how to work out how many moles we've got present if we've got that amount of substance, and then also to be able to work in the other direction as well. So this is all about scaling. So just like we've done previously, we need to scale through 1, and we need to start from our key fact. Now you don't need to write any of this down. We've got more examples on the PowerPoint to go and put into your theory notes, so this is an additional one here. So in order to start our question, we need to decipher our key fact. So what we know about our hydrochloric acid is our concentration, and we want to know how many moles we have got in that 25 centimeters cubed. So we know we've got 0.2 moles in 1,000 centimeters cubed in 1 dm cubed, and we're aiming for a new volume to find the number of moles in that. So we're going to scale through the volume because we know all about that. So we can say as our key fact that if we had 1,000 centimeters cubed of this stuff, we would have 0.2 moles. But we don't have 1,000 centimetres cubed, we've got 25 centimetres cubed. And I've deliberately left that line in between so that we can go through one. So 1 centimetre cubed is going to be 0.2 over 1,000 moles. Remember, 1,000 down to 1, divide by 1,000. So we do the same on this side. And then 1 to 25, we're going to multiply up by 25. And then we would put that into our calculator. So that gives us 0.005 moles. So we have just calculated how many moles we would have if we have 25 centimetres cubed of 0.2 mole per dm cubed HCl. And that is a very similar looking calculation to when we've used moles and masses and we've used moles and gases. So we start with our key fact and then we work our way to what we're trying to find out. Now we can also go in the opposite direction. So when we're making up solutions, we might start by having a certain number of moles and dissolving it in a certain volume. So for example, again, when the technicians make up solutions for us, they never make up 1,000 centimetres cubed. They might make up like 8,000 centimetres cubed to go around all of the different classes. So we rarely actually aim for that 1,000. It could be different quantities. So we need to know how to work out the concentration. So we could say, for example, what is the concentration when 0.3 moles of HCl are dissolved in, what should we say? Let's say 50 centimetres cubed of water. Now, we're asked to find the concentration, so what we need to do here is scale so that we can end up knowing how many moles we would have if we had 1,000 centimetres cubed. So we're starting from 0.3 and 50 centimetres cubed, so they are our key facts here, so this is where we need to start from. Again, we're scaling up to 1,000 centimetres cubed, so because we're scaling from a volume to a volume, we'll put the volumes on the left hand side. So we know from the question that 50 centimetres cubed of water contains 0.3 moles of HCl. Concentration, we've said, is moles in 1,000 centimetres cubed, same as moles in 1 dm cubed. And so we're going to scale accordingly. We're going to go through one, even at the moment with numbers that look fairly nice, and you could probably go straight from 50 to 1,000. Make yourself go through one, because then when they're horrible numbers, then you'll know the method, it'll be stuck in your head. So to go from 50 down to 1, we divide by 50. So any number divided by itself is 1. So we do the same on the other side. So 0.3 over 50. And then to get from 1 centimetre cubed to 1,000, we just multiply it by 1,000. So 0.3 over 50 times by 1,000. And then we pop that into our calculator. This is one where I really should have done a bleepy to his one I did earlier. But if we put that in our calculators, we end up with 6 moles. Now we need to make sure we quote this with our units, but this line, we can't change the units because we've just scaled from volume and moles to volume and moles. So our final conclusion needs to say that because we've got 6 moles in 1,000 centimetres cubed, our concentration, our conc, is equal to 6 moles dm to the minus 3. Whoops, that's the screen. Let me move that over for you. Okay, so again, it's just the scaling kind of idea that we've introduced before. It's pairing up the bits of information that we know and letting ourselves use that, go through one to get to the thing that we need to find out, so to get to our unknown. So here we paired the volume and the concentration that we were given in the question, and then we worked our way up to 1,000 to work out what the concentration was. And then remember, in our first step, we knew what the concentration was, so we paired up 1,000 centimetres cubed with moles, and we went through one to work out the number of moles in the volume that we were being asked about.